the sun in that case. In that case, the tip of the umbra doesn't make it to the ground. It flies above the surface instead of moving along the ground. So nobody gets to see a total eclipse in that case. There are people that will travel. I would travel to see a total eclipse. I did. There are people that travel to see annular eclipses. I wouldn't do that. I mean, it's great and all that, but it's just nothing compared to a total eclipse. And I don't have that kind of cash. So if I had more cash, I'd be like an umbrophile, an eclipse chaser. I don't have that kind of cash. Okay, what next? Yeah.
Can you just like give us like an example of something that could be on the exam tomorrow?
An example of what?
Something could be on the exam tomorrow? Like,
Well, anything on the study guide could be on the exam. I'll tell you that there's 40 multiple choice questions and then 4 multi-part short answer type questions.
like straight out of the lecture notes?
Yeah, so basically, there's some that are based on lecture tutorials. There's some moon phase wheel ones that are in that. That's what you want to, basically you definitely, to get ready for that part, you've got to look over your lecture tutorials. Be sure you can do the moon phase wheel stuff. Be sure you look at the visual quizzes on mastering astronomy, because I like to throw questions similar to those on as part of the multiple choice
So if we
questions.
study the visual concept reading, we'll be all right?
Well, basically, I don't want to say, just study this and you'll be fine. But go over the study guide, the lecture tutorials, the mastering astronomy, and then I would say go through the visual quizzes on mastering astronomy, which are part of the assignments anyway, at least the last one, I think. But you can always get to them. The concept, visual quizzes, reading quizzes, those can all be helpful because they're similar to the questions that I ask as multiple choice questions.
The same.
So they're good practice. Sometimes they are, but sometimes I'll give it a twist. I'll change the phase of the moon in my question, or I'll change it to the southern hemisphere instead of the northern hemisphere or something. Because I want you to understand the concepts involved, not just memorize them. Yes.
Could you explain what Tycho?
Tycho, yeah.
What his contribution was?
Yeah, so Tycho, his big contribution was being the greatest naked eye astronomer ever. And in particular, his detailed observations of planet positions. Hi Tycho, how are you? His detailed observations of planet positions using his large naked eye instruments are what allowed, with Mars in particular, Johannes Kepler, his assistant, to realize that circles or combination of circles for the orbits of the planets would not be able to reproduce Tycho's observations. And Kepler could have just chalked it up to Tycho having made observational errors, but he was confident that Tycho was a good enough observer that it was real. And that's what allowed him to hit upon the idea, you know what, I can make this work if I use ellipses. And so he formulated the 3 laws of motion for which he's now famous. So Tycho fed into that. It was with Tycho's observations what allowed Kepler to formulate his 3 laws of planetary motion.
There's something in the book about like measuring angle with your hand outreached.
Yeah.
It's in the book.
Yeah, right, and so that you can use that to approximate angles on the sky. And we didn't do any of that, so I'm not going to hold you responsible for it. But it is good to know your outstretched hand is like, 5 degrees across or something like that. It's a way to estimate angles on the celestial sphere. Yeah.
What about that raisin cake question? You think that'll be on there?
That's not going to be there because the raisin cake was for the expansion of the universe. And first of all, that's Astronomy 111. And second of all, I'm not putting that chapter 1 stuff on the exam. So no, raisin cake's not in there. Sad but true. Yes?
Can you go through the angular measures of the degrees, minutes, and pounds?
Yeah, that's actually not too hard because it's very similar to on a clock. So if I have an hour on a clock, how many minutes are in that? Yep, 60 minutes an hour. And how many seconds are in a minute of time? Okay, yeah, you know, right? How many seconds are in a minute of time? I'm not, you know, it's not a trick question. 60, right? Yeah, okay, yeah. So it's very similar with degrees. How many minutes of arc are in 1 degree of arc? 60. And how many seconds of arc are in 1 minute of arc of angle? 60. So it works the same way. It works the same way. That's not to say that the seconds on the clock are 1 arc second apart from one another, because that's time measured on the clock. It's not angled directly. A second of arc is 1/3600th of a degree. It's a tiny, tiny little angle. The moon in our sky is about half a degree in angle. About 30 minutes of arc in angle is how big the moon is in our sky, how big it appears to us. So yeah, I want you to know that there are 60 minutes in a degree and 60 seconds in a minute when you're talking about angles.
Okay.
Yeah. Yes?
How could we interpret or use declination without having a celestial globe in front of us?
By having a photograph that I took of a celestial globe. Yeah.
Will you review that with us, please?
Sure, because in fact I will tell you, I've got some photographs that I took of the celestial globe, and then you get to, you know, figure out things from that, basically. So remember that, which one of them is celestial latitude? North-south. Is it right ascension or declination? Declination is celestial latitude, north-south. Where is the declination 0? In other words, what are we measuring declination away from? The celestial equator, yeah. So the celestial equator, everywhere along it, the declination is 0. And on my globe here, I'm sure you can see it from back there, you may recall we have this declination scale where there's a 0 hovering above the celestial equator there to say that that's 0 degrees declination. How about the North Celestial Pole? What is its declination? What angle is it? 90 degrees away, as seen from the center, 90 degrees away is the declination of the North Celestial Pole. What about the declination of the South Celestial Pole? 90 also, but how do we distinguish them? We say that the North Celestial Pole's declination is positive 90, and we say that the South Celestial Pole's declination is negative 90. That's just a convention related to the fact that the people that came up with it lived in the northern hemisphere. If they lived in the southern hemisphere, south would be up, positive declinations would be southern declinations, and so on and so forth. But they're not, because of that historical accident. So the other thing is, it's helpful to remember that on these globes, you could do it differently, but on these globes, all of these circles that are parallel to the celestial equator are 10 degrees declination apart from one another. So everywhere along this circle that I'm tracing my finger is 10 degrees north declination, plus 10. Everywhere along this circle is minus 10, plus 20, plus 30, plus 40, plus 50, plus 60, plus 70, plus 80, plus 90. And then minus on the other side. So if I showed you a picture, and I had, for example, here's the star Deneb, and I said, look at that picture, tell me what its declination is, you would say, you know what? All these circles are 10 degrees apart, and here's the celestial equator, so I just go up 10 degrees, 20 degrees, 30 degrees, 40 degrees. 40 degrees is too small, but 50 degrees is too big, so it's about 45 or 46, and I wouldn't split hairs, it's not, well, you said 46, it's really 45.3, no, I'm not going to do something like that, as long as you're within a degree or two, as long as I can see, what you're talking about, that would be fine, as far as that's concerned. Okay, so any questions about the declination? Yeah.
When we use the equation 90 minus that,
so that was the business where, to figure out the circumpolar region, right? So in other words, the idea there is, I was asking you things like, if you're at a latitude of, well, let's just pick ours. What's about our latitude? 40, yeah. And so I could say, what range of declinations is circumpolar? The stars are always above our horizon. Well, I can actually figure it out just by drawing a picture here. I don't even need a celestial globe to really do this. Let's say that we're at 40 degrees north latitude. There's the north celestial pole. What is here? It sits right above the northern part of the horizon, the north point on the horizon. What's that angle right there? I mean, it's a distance that I've drawn on the board there, but in other words, if I think of, I point to the pole, I drop my arm parallel to the horizon, I point to the ground, what angle did my arm go through if our latitude is 40 degrees? The altitude of the celestial pole is equal to your latitude. So if I'm at 40 degrees north latitude, what's that angle? 40 degrees. So that's 40 degrees right there. So we're at latitude 40 degrees north. That angle would be 40 degrees. Quick, if our latitude was 20 degrees north, what would that angle be? 20. What if we were at 30 degrees south? Could you see the north celestial pole? No, because it would be 30 degrees below the horizon, hidden by the ground. So, I want to know what range of stars is circumpolar. My circle's probably going to suck. Pretend I'm drawing a really beautiful, perfect circle around the north celestial pole. Oh, look, isn't it beautiful? Wow. Almost, oh, it sucked. Just like I predicted. Okay, there, that's supposed to be a beautiful, perfect circle centered on the north celestial pole. That's really bad, but I'm going to resist the urge to get rid of it. What is the declination? So what is the declination of the north celestial pole? 90, right? So, its declination is plus 90 degrees. Its altitude is 40 degrees. So notice, if I had a star that was on that circle, what would I see it do as the Earth turned? It would circle around the pole, right? So that star would circle all the time around the north celestial pole. And what we can conclude is any star that is closer than 40 degrees from the north celestial pole is circumpolar. Every star within 40 degrees of the NCP never sets. It's circumpolar. Well, what declination then must this circle have? It's 40 degrees away from 90 degrees. What's its declination? 50 degrees. So the range is 50 degrees to 90 degrees for stars that are circumpolar. Notice 50 degrees here was 90 degrees minus our latitude. That's where that's coming from. 90 degrees minus your latitude, because your latitude is how high the pole is above the ground, and as long as you're within that angle of the pole, which has declination of 90 degrees, you will be circumpolar. So 90 degrees minus your latitude is where the range starts, and it always goes up to 90. Unless you're in the southern hemisphere, then you replace those with minus signs. Any questions about that? All right, what next? for my altitude of my pole to be 30 degrees, what would my latitude be? 30. And then what would the range be instead of 90 minus 40 to 90? It would be 90 minus 30 to 90. It would be 60 degrees to 90 degrees if you were at 30 degrees latitude. Because you'd have to be within 30 degrees of the pole to be circumpolar. So whatever your latitude is, you have to be within that many degrees of the pole in order to be circumpolar. So the further north you go, the higher the pole gets, the more of your sky is circumpolar. Santa Claus has the entire northern hemisphere circumpolar. Everything above the equator, north of the equator is circumpolar, because Santa is at 90 degrees latitude on the North Pole, and that means the North Celestial Pole is straight overhead, and the circumpolar zone goes all the way from the celestial equator to 90 degrees. It'd be 90 minus 90 is 0 for the starting declination. Yes.
So, Copernicus started the sun center, but kept it in perfect circles. So
Yeah.
planets orbit the Earth in perfect circles. But how does that still explain retrograde motion?
The only thing that matters for the retrograde motion is that for the correct explanation of retrograde motion is the idea that both the Earth and the other planet are orbiting the sun, and that the Earth can overtake the other planet, or if the other planet is a so-called inferior planet, closer to the sun than us, it can overtake us. So it doesn't matter whether the orbit is circular or elliptical. The fundamental thing that happens, as long as you have a sun-centered model, is that you get, let's see, you get, come on. There's a lot of slides here, aren't there? There we go. You get this idea of Earth can pass Mars and cause Mars to appear to go backwards for a while we're passing it. That's the retrograde motion, is when the planet looks like it's going backwards, but it's really just that we're passing it. And notice, this video from Perkins that I showed everybody in class, it has the planets going on circular orbits. So that was, and Kepler, Copernicus wasn't the first person to think of this. There we go. Wasn't the first person to think of this, but in other words, there's Earth overtaking Mars, and the line of sight is tipping backwards for a while as a result of that. Doesn't matter if it's circular, elliptical, whatever, it'll still work. That's how we understand retrograde motion now, is that that's what's happening. Whereas the ancients, Ptolemy had it as this complicated model of circles on circles, and the planet was literally moving backwards. So does that make sense?
Yeah.
Okay. Are you asking me like 10, 11, 12? Is that what you mean? Okay, yeah. Does anybody ask any more questions, or are we done? Looks like we're done. Okay, I'm gonna go stop the video and we can talk about it.